My name is Hayden Hubert. I'm going into my sophomore year of my physics BS at Spelman College, and this summer I did my project on enhancing existing linear full waveform technology for improved radiometric measurement with the Geospatial Research Lab in ERDC. So LiDAR uses a pulsed laser to create 3D maps for various imaging applications. The Geospatial Research Lab is developing a multispectral LiDAR that captures data across multiple different wavelengths. This project aims to upgrade, develop, and gather data using a linear full waveform LiDAR for comparison of intensity with a Geiger mode avalanche photodiode multispectral LiDAR performance. The main objectives of my project were to upgrade an existing linear full waveform LiDAR system to be more efficient and compact. Number 2 was to receive and analyze intensities obtained using the linear full waveform LiDAR. And then number 3 was to benchmark the data obtained from the linear full waveform LiDAR with spectrometer measurements. So for number 1, I basically inherited a former project of my mentors and was tasked with optimizing this to collect intensity information. So for the first upgrades of the system that I inherited, I wanted to make the system to be more efficient and compact. So this is a schematic of my original project, and this is a picture. But I basically took the collection lens that we were using to collect scattered light and replaced it with a upgraded collection lens. So the original collection lens was a 20 centimeter diameter collection lens with a focal length of about 80 centimeters. And the upgraded collection lens was a 7.5 centimeter collection lens with a focal length of about 7 centimeters. So that already accomplished the objective to make the system more compact, because I was able to remove 2 mirrors that were assisting the collection lens in imaging onto the silicon photomultiplier, which was detecting intensities from our laser. So that was the first objective of making it more compact. And then we used the SIPM, which was a silicon photomultiplier, and an oscilloscope to detect the signal. And we found that the upgraded collection lens was getting a intensity information of about 17% less of the original system. And even though it was giving us about 17% less, it was still operating at a higher rate than the original system was. So we accomplished the first objective. And then for number 2, we wanted to make sure that we were actually getting a signal from this laser system. So using the SIPM and the oscilloscope, we used varying reflective targets, which were 99%, 75, 50, 20, and 2%. And we basically looked at the system, the oscilloscope, and the SIPM, and we found that we were actually receiving intensity information, and they were corresponding with their varying reflectivities. And so that was the second objective accomplished. And then third, we wanted to ensure that the reflective targets were actually reflecting at the rate that they were claiming to be reflecting at. So we used a spectrometer and changed out the varying reflective targets, and the spectrometer basically gave us a very broad range of what the reflective targets were reflecting at for different wavelengths. So from 0 to 110 nanometers, it told us what these reflective targets, the rate that they were actually reflecting at for the varying wavelengths. So we were using a 980 nanometer LiDAR, so we looked at that 980 nanometer wavelength, and we found that it was reflecting at about a higher percentage, but we calculated the margin of error and found that the targets were reflecting within their margin of error, and so that they were a reliable signal. So we did this with all of the reflective targets, and we found that they were all reflecting at between the margin of error, and they were all accurate and reliable signals. So that was my project this year with Dr. Tariq Ahmido and Ms. Natasha Zimmerman. Thank you.